What appears to be an empty space is actually a tumultuous ocean of strings, vibrating at the precise frequencies, creating the four dimensions height, width, space, and time. And this is what string theory comprises of. Adar, adab, abhinandan, abhar. Hello, and a very good evening to everyone present here. Welcome you all to the fourth session of virtual guest lecture series of Celesta 2020, the annual techno management exuberance of IIT Patna. This year, amidst the pandemic circumstances, we have gone entirely virtual. But you don't need to worry about because we have promised to give you an unparalleled experience. So call out your friends and get glued to the screens because the ride is definitely going to get you hashtag excited. You guys may still be wondering what a spooky code did I start with? Well, today's talk demanded it, and that's nothing compared to the sea of knowledge possessed by the personality we are gonna hear today. A theoretical physicist at Tata Institute of Fundamental Research, Mumbai, renowned for his pioneering work in string theory and quantum field theory. He did his master's in physics from IIT Kanpur in 1995 and was awarded the President's Gold Medal for securing the highest CPI. After completing his PhD in physics from Princeton University, he served as a junior fellow and assistant professor at Harvard University. He had uncovered an unexpected connection between the equations of fluid and superfluid dynamics and Einstein's equations of general relativity. And these influential contributions have won him several prestigious awards, including the Shanti Swarup Bhatnagar Award 2011, Infosys Prize in Physical Sciences in 2013, TWAS Prize in 2016. Well, I couldn't list that all as there are many, and this great personality indeed deserves it all. So, all the science lovers and astronomy geeks, tighten your seatbelts, because here's to tell you about the search for quantum gravity, a leader in the quantum gravity research. Please welcome Dr. Shiraz Minwalla. So,
Hi, can you
warm
hear me?
greetings, sir. How are you?
Very good. Let me see. Are you able to see my screen at the moment?
Yes, it's completely fine, sir.
It's fine. Um,
Yes. So,
I'm not able to go into full screen mode. I'll just stop sharing and start again.
no, sir, it's visible, sir. It was.
It was, I'm sorry, but I wasn't
Okay.
able to move onto full screen somehow.
So, no, you can try now.
Yes. Now maybe you see my desk. Are you seeing something?
Not yet, sir.
Oh, I'm sorry if I messed this up.
No, no, it's no problem. So you can just go to the third button here in this uh, beside the
Okay.
video one.
Application video. Share. Okay, forget this full screen then. Let's just do this. Okay, so let's start. Can you see this?
So yes, it's on full screen. So sir, let
Okay.
me do this.
Yeah. Okay,
So
excellent. So let's go. Okay, so thank you very much for your invitation. It's great to visit you guys at IIT Patna virtually. It would be even more fun to visit you physically, but maybe that's at a separate occasion. My talk today is titled "The Search for Quantum Gravity," and these are the sort of suggested contents for this talk. I'm going to spend a fair amount of time, maybe 15 minutes, maybe 15 or 20 minutes, telling you about the question. What do I mean by the search for quantum gravity? What is the question we're trying to answer? I will then take you very quickly through what some people call the string framework, and then come to the main part of my talk, namely to explain to you one complete model with quantum space-time. I'll then end with some future outlook and conclusions. Okay, so let's start. As many of you know, maybe all of you know, theoretical physicists over the last few hundred years have developed increasingly sophisticated mathematical models that now, taken as a whole, describe an astoundingly wide variety of physical phenomena. Now, something that I find even more interesting about this state of affairs is that the mathematical models that capture physical phenomena display a great deal of unity in formalism and unity in structure. By this I mean the following. There are a handful of basic frameworks that, and by framework I mean a fundamental mathematical and interpretative structure that underlie all the models of theoretical physics. So you take a model of, let's say, the helium atom, or a model of a conductor in a laboratory. These are very different systems with very different numbers of degrees of freedom, very different scales, and yet the basic framework for the model of the helium atom is the same as the basic framework for the model of your conductor. And in this case, the framework is that of quantum mechanics obeying Schrodinger's equations. Okay, so this is an example of the fact that there are these few basic frameworks that underlie all of our modeling of reality in physics. And this unity, this fact that there is, there are these few structures that end up modeling so many zillions of apparently unrelated phenomena, is quite remarkable and one of the wonderful things about our scientific description of the world. Now, in this talk, two of these frameworks will play an important role. The first of these we've already alluded to. It's the framework of quantum mechanics, or the quantum framework. This framework was developed between 1900 and 1930, and it is the basic grammar, the basic mathematical structure that has been used in particular in the construction of all models of particle physics over the last 80 years. Okay, so our theories of elementary particle physics are set within the quantum framework. Let me say this in a little more detail. Modern theories of elementary particle physics are set within a sort of specialization of the quantum framework called quantum field theory. So what is quantum field theory? I will give you a 2-minute introduction to what it is. Within quantum field theory, okay, so quantum field theory, the first thing to say about quantum field theory is that it lives in space and time. Okay? The second thing to say about quantum field theory is that the space and time in which quantum field theory lives is a passive stage. It's a grid that is set up once and for all, and all the dynamics of quantum field theory happens on this grid. This grid is just some sort of scaffolding which hosts dynamics. It does not participate in the dynamics of a quantum field theory. The next thing to say about quantum field theories is that the number of quantum degrees of freedom in a quantum field theory are infinite in number. But this infinity is not a completely uncontrolled infinity. It has a certain structure. At each point in space in a quantum field theory, we have one or a finite number of degrees of freedom. And then because of that, we get an infinite number of degrees of freedom, just because there are an infinite number of points in space. So this infinity of the number of degrees of freedom is in one-to-one correspondence with the number of points in space. And interactions between different degrees of freedom are local, in the sense that degrees of freedom here interact only with degrees of freedom nearby, and interactions from here to here to here to here, and moving on further away, only happen through exciting intermediate degrees of freedom. Okay, so this is what a quantum field theory is. A quantum field theory is a quantum system. It lives in a background space-time that is dynamical, that is non-dynamical. It's a grid, it's a stage, it's set once and for all. Okay, and the theory has an infinite number of degrees of freedom. Interactions are local. This is the first framework that will play a role in my talk. The second framework that will play a role in my talk is the framework of what is called the framework of the general theory of relativity. Okay, so within this framework, this is the framework that is used in all descriptions of modern theories of cosmology. Okay, theories of the origin and evolution of the universe as a whole. Within this framework, um, so I'm going to give you 2 minutes about this framework. In this framework, we also have space and time, as we did in the case of a quantum field theory. Okay? However, there is one big difference between the space and time in the general theory of relativity and the space and time in a quantum field theory. In a quantum field theory, space and time is an unmoving, unchanging grid specified once and for all before we start doing dynamics of our stuff. Within the general theory of relativity, space and time, or more precisely, the geometry of space and time, is not a pre-specified thing, but is a dynamical variable by itself. So the geometry of space and time has its own dynamics. It ripples, it moves. It affects the dynamics of matter that is moving around inside the space-time, but is also affected by the matter that is moving around inside the space-time. Okay? So it's a true participant in the dynamics of the universe. So that's the first thing to say about the general theory of relativity. Space and time in this theory is dynamic. The second thing to say about the general theory of relativity is that it is a classical field theory. So what do I mean by that? What I mean by that is that this theory, just like the quantum field theory, has an infinite number of degrees of freedom, one or a finite number of which are associated with each point in space. But unlike in a quantum field theory, these classical degrees of freedom are not operator valued degrees of freedom like in a quantum field theory. They're just numbers. Okay? So the mathematical framework for classical field theory is just differential equations. You're keeping track of a finite number of numbers, one at each point in space, so that's a function of space, and you're seeing how it evolves in time according to differential equations. Okay? So here we have it. We've seen two frameworks. Quantum field theory, set in an unmoving background space-time with degrees of freedom in quantum degrees of freedom in each point in space interacting locally. And then you have the general theory of relativity, also a field theory, also an infinite number of degrees of freedom, one or a few for each point in space-time, interacting locally. One difference here is that these degrees of freedom for general relativity are classical; they're just numbers. Second difference is that the space and time in the general theory of relativity is dynamical, unlike in the quantum field theory where it's just a grid. Okay, so these two frameworks that I've talked about have by themselves been extremely successful. Quantum field theory has been spectacularly successful in describing subatomic scale physics, particle physics. In particular, in this slide, I've quoted a prediction from an experiment for some quantity. Doesn't matter exactly what. And so this is the prediction from theory for this quantity, and the measurement from experiment for the same quantity, and it agrees to a remarkable number of digits. Okay, this shows how successful the framework of quantum field theory is in correctly predicting subatomic scale phenomena in our world. On the other hand, the general theory of relativity, the second framework, has also been spectacularly successful in describing astrophysical and cosmological dynamics, from scales ranging from kilometers to the size of the universe. In particular, as I've already said, the general theory of relativity has been used with great success in understanding the evolution of the universe as a whole. Okay, so we've got these two different frameworks. Quantum field theory, very successful in describing subatomic scale physics. General relativity, very successful in describing astrophysical phenomena, planetary phenomena, dynamics of the universe as a whole. However, the situation, which so far sounds very good, everything I've talked to you about is successes. The situation is still not what it should be. Because, as you've seen from my description of these two frameworks, quantum field theories appear to ignore an important aspect of reality, namely that space-time, or more precisely the geometry of space and time, itself is dynamical. How do we know that this is dynamic? It's dynamical. We know this because of the success of, let's say, cosmological or astrophysical predictions from the general theory of relativity, where the dynamics of space-time is a key ingredient. On the other hand, general theory of relativity, which does not ignore the dynamical nature of space and time, ignores something else. It ignores the fact that the real world is quantum. Degrees of freedom in the world are not classical, but they're quantum. How do we know they're quantum? Well, experiments over the last 100 years have demonstrated without a doubt that degrees of freedom, small degrees of freedom, behave in a quantum way. So you see, both quantum field theory as well as general theory of relativity ignore a crucial aspect that we know to be true of the real world. Quantum field theory ignores the dynamical nature of space and time. General theory of relativity ignores the quantum nature of reality. This is not satisfactory, right? I mean, some of you don't need any more convincing. Some of you feel that, well, okay, if there's a feature of the real world, and we don't have, if there are two features of the real world, but we don't have one framework which incorporates both of these features, not satisfactory. We need a better framework for doing physics. But some of you may be more practical-minded and may wonder, okay, it's all very well that we don't have a single framework that describes everything, but is there a phenomenon of interest, some phenomenon we are interested in studying, in which quantum field theory or general relativity or some union of the two are not sufficient to describe dynamics? Well, what kind of phenomenon can we not describe with quantum field theory? One in which space-time is dynamical. What kind of phenomenon can we not describe within general relativity? One in which the quantum nature of reality is important. So if you've got a phenomenon in which both the dynamical nature of the world, of space-time, as well as the quantum nature of things, but especially of space-time itself, become important, then neither the framework of general relativity nor the framework of quantum field theory would be sufficient to describe this phenomenon. You could ask, is there any such phenomenon that is of interest? And there is, of course, one phenomenon that is of great interest to, I think, basically every thinking human being, and that is the birth of the universe. So let me explain what I mean. Let me take 2 minutes to explain what I mean by this. As you know, when we look out into the universe with our telescopes and of very sophisticated sorts, what we see is a slice of the universe at a given time, more precisely a given light cone time. As we look further and further out, we see what the galaxies are now, or really were at the time when the light left them. Looking at it. Now, from this, you could ask the question, what was the universe like at earlier times? Now, how could we answer such a question? We can't see what it was like at earlier times. We only see one slice of the universe now. How can we figure out what the universe was like at times that don't lie on the slice that we can see? This is what, well, in order to do that, what we use is the equations of physics. You see, the equations of physics are designed for the following problem. You take what you see now and use the present to predict the future. That's what physics is good for. But it's a great fact about physics that all the fundamental laws of physics, so far as we understand, work as well in future time as in backward time. So, although we are usually in physics interested in taking the present and predicting what will happen, predicting, for instance, the outcome of an experiment, we can as well use the laws of physics to take what we see in the present and post-predict the past, figure out what the past was like. And that's what's done in theories of cosmology. So what is done is you take the universe as we see it now and use that as initial conditions for backward evolution in time to try to figure out what the universe was at earlier times. So what we see today is that the universe is filled with these galaxies that are moving away from us faster and faster as the galaxies are further and further away. When you take these initial conditions, put them into the appropriate equations of cosmology, you can figure out what happened at earlier times. And pictorially, you can sort of use the equations of physics to, in your mind, create a movie of the universe as you run the clock backwards. First, let's see what the universe is like as we run the clock forwards. We see these galaxies, they're all moving further and further away from us. So it's going further, faster and faster as you go. Okay, so the universe is going like this. But if you take that same initial condition, run the clock backwards, the galaxies now in negative time start going towards each other. They're going nearer, 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 nearer. And then there is a time around 14 billion years ago when things start getting really interesting, when everything we see in the universe today is crunched up into some very small little volume. A small little space, smaller than, let's say, the 15th of a meter, 10 to the power minus 15 meters. Perhaps smaller than that. Now is when things are getting really interesting, right? Everything that we see now had its origin in some very small region. And you can ask, what happens before that? And the answer is we don't know. The reason we don't know is that the way we figured out what happened in backward time was by using the laws of physics. Once we get to this strange place where matter is crunched together, matter and energy is crunched together into this very small volume of space-time, the equations of physics as we understand them become uncertain. And we can't use them to run the movie further back. In order to run the movie even further back, to get to the really interesting part, to answer the question like, did the universe have a beginning? If so, how did it begin? Or if this wasn't the beginning, what happened before this thing? We need better equations of physics. And in particular, we're likely to need a quantum theory of gravity, a theory in which that can handle phenomena in which quantum mechanics and the dynamical nature of space-time are both simultaneously very important. Okay, so this is my offering to you for why it is interesting to look for a quantum theory of gravity. We lack it. We do not have a good theoretical framework within which we can study phenomena in which the dynamical nature of space-time and the quantum nature of anything, but in particular space-time, are simultaneously important. And we must try to look for one, because it seems very likely that that interesting questions, like questions about the birth of the universe, we will not be able to make decisive progress on these questions unless we have such a framework. Okay, so hopefully you are all motivated now. You all agree with me that the search for the quantum theory of gravity is an interesting and important search that humanity must undertake. This has, of course, been clear to everyone for a long time. Maybe Dirac, the late 1920s, was already trying in some way to find a quantum theory of gravity. It's been 90 years since then, and progress has been very limited. Why has that been the case? Many very smart people have spent their whole lives, large parts of their lives, trying to find this theory, and progress has been sort of limited. We don't yet have the quantum theory of gravity of our world. Why not? Well, you see, the search for the quantum theory of gravity has been limited by an unfortunate phenomenon. Quantum fluctuations of space, time, and geometry are important only at very small length scales. Now, traditionally in particle physics, we search for things at very small length scales by taking two things and banging them together very hard. For instance, like in the LHC experiment at CERN, which I've got a picture of in my slide. However, though this fantastic LHC experiment at CERN goes to very, very high energies, our best guess estimates suggest that in order to reach distance scales that are so small that we would be able to directly experimentally probe quantum fluctuations of space-time, we would have to go to energy scales that are much, much larger. Something like 10 to the power 15 times larger, or 10 to the power 18, depends on various details, larger. And such a large jump in energies is a very, very technologically very, very difficult thing to do. And it's almost certainly not going to happen in my lifetime. Okay? So it's very hard to design accelerator experiments that probe the short distances that we would need, that we need to access in order to probe the quantum fluctuations of space-time. Okay, if accelerator experiments don't work, maybe we can use other observations or experiments to try to probe what happens in quantum gravity. Where can we look? Well, I've already told you that that it's very likely that sizable quantum fluctuations of space and time, geometry, were important in the very early universe. If that's the case, then these fluctuations that were important in the very early universe should have left their imprint on the universe that we see today. So if we were smart enough, we could make detailed observations of the universe as we see it today, and from that figure out what the quantum fluctuations of space and time were like in the very early universe. However, half a minute's thought will tell you that this is going to be a very difficult job. You see, a lot has happened in the last 14 billion years. Matter has sort of condensed out of energy. There's been this deconfinement transition. Galaxies have formed, black holes have formed, Earth has formed, all kinds of things have happened in the middle. Lots of interesting dynamics has happened. And what we see in the universe reflects all of this. To unentangle this and to go back, to undo this dynamics and figure out what were the quantum fluctuations of the universe at a very early time is clearly not going to be an easy thing to do. Actually, it's less difficult. Some parts of it are less difficult than you might think, because of this remarkable theory called the theory of inflation. And there is some hope that we'll get some information this way. But in general, to get lots of detailed information with quantum gravity clearly will be a very difficult thing to do. Fine. Now, other regions of the universe where quantum fluctuations of space and time are qualitatively important, apart from the very early universe, exist. We believe that at the center of black holes, quantum fluctuations of space-time are very important. However, there's another unfortunate fact about these regions. You see, the center of a black hole is cloaked by an event horizon. And the event horizon is a sort of a one-way door. You can get in, but you can't come out, at least classically. What this means is the following. Suppose you were a very cruel advisor and you sent your PhD student into a nearby black hole with a lot of sophisticated instruments and asked her to note them down and to collect the data needed to construct a quantum theory of gravity, because she would have access to what's happening just near the singularity. And suppose you had a student who would be willing to go. Well, the student would perhaps be able to make all these measurements, but she'd never be able to publish her results, because she'd never be able to send the information back out outside the black hole before she meets her untimely end at the center. Okay, so we tried particle accelerator experiments. We couldn't reach the energies needed. The early universe is a possible source of information, but it was very long ago and lots has happened since then. So it's hard to figure out, to go back and get information. Centers of black holes are promising places, but they're cloaked by event horizons. So even if we could see them, if we could send someone in to look at them, or let's say a robot in to look at them, the robot won't be able to send us the information back out. So as you see from these three examples, and of course people have tried many other ideas, we're constrained to embark on our quest for the quantum theory of gravity with very limited guidance from experiment. Okay, so we, traditionally in physics, we gather data from experiment, and then we try to use our minds to find a theory to explain the data. Here we're in the strange situation. We have a question which we know to be an interesting question, but we have very little data. What should we do in such a situation? Well, there are two possible attitudes one could take. One attitude is the pragmatic attitude. A completely pragmatic race of intelligent beings might say, well, this is an interesting question, but not one that we can meaningfully tackle with our current state of technology. So we'll come back to it in 1,000 years when we have more information and we can make more meaningful progress. That would be one reasonable attitude to take. Thankfully, humans are not reasonable people. When faced with a question that seems very interesting, no physicist worth, if that physicist finds that question really interesting, no physicist worth his or her salt would say, well, let's wait 1,000 years. You want to answer it and you want to answer it now. And you want to make some progress on it. You want to do something about it to see. So what physicists, the route that physicists have taken over the last 40 or 50 years is to adopt an alternate strategy, a strategy sometimes called the strategy of the spherical cup. Now, so let me tell you, for those of you who have not heard this story, let me tell you this. This is a story about the spherical cow. This little story, which is meant to be a joke, goes as follows. Where there's a farmer who has this excellent cow who's giving a great deal of milk every day. But one day, she stops giving as much milk as before. Now, the farmer gets worried. Her prize cow is not giving her the milk he expects, and he thinks something is wrong. Luckily, this farmer has a Nobel Prize-winning physicist as a friend. So the farmer thinks, this lady, my physicist friend, is a very, very intelligent lady. Maybe she can help me. So he calls the lady over and says, Professor, my cow is not giving enough milk, and I don't know what the matter is. Can you try to figure it out? And the lady thinks and says, the scientist thinks and says, this is a complicated question. To start with, let me model your cow as a sphere. Now, the farmer doesn't know very much mathematics, but he knows what a sphere is. He looks at his cow, he thinks of a sphere, and then he turns to the professor and says, thank you for your time. I'll manage on my own, and says, bye-bye. Okay. This story is, of course, a joke, but it's a serious joke. It's a serious joke in the sense that it illustrates the way theoretical physicists tackle problems. You see, sometimes some phenomena are very complicated phenomena. In this case, the phenomenon was the phenomenon of the cow not being able to give enough milk. It's so complicated that it's hard to try to make a mathematical model of every aspect of this phenomenon. Okay, so hard that, such a model can only occur on a computer keeping track of zillions of degrees of freedom. You don't want to learn very much by doing that, even if you could. On the other hand, what happens in many phenomena is that while to get every detail right, you need a very complicated model. The essence of the phenomenon is contained in a simpler model, which you can mathematically model. And physicists constantly do this. They constantly take some phenomenon and try to abstract away the key features of it, put those features into a model and try to solve that model in order to try to understand that phenomenon better. Then you can complicate your model to try to make further progress. Okay, so this is what physicists have done for the problem of quantum gravity. The problem sounds very interesting, but it sounds very difficult. We don't yet know how to make progress. So in order to try to make progress, physicists, and especially string theorists, have adopted the following strategy. The strategy is one of retreat. We don't know how to make progress in finding the theory of quantum gravity that governs quantum fluctuations in our world. So instead, what we've decided to do is to retreat a bit. To instead ask the question, can we find any mathematical consistent theory that contains in it both quantum mechanics and gravity? That is, any mathematically consistent theory that is quantum mechanical and reduces at long distances to the general theory of relativity, interacting with various fields. Now, you might think that that is quite a retreat, because the distance between any consistent mathematical theory of quantum gravity and the theory that governs the physics of the world we live in may be a big one, and it is quite a retreat. However, one thing makes it less stupid strategy than you might think, and that is even this weakened goal of finding any consistent theory of quantum gravity that is just consistent, that is just logically consistent. Even that weakened goal has proved to be a very difficult one. And the only real progress, the only truly sharp progress, only one complete example. The first complete example of finding such a model happened, in my opinion, in 1997, by a physicist called Maldacena, a then young Argentinian physicist named Maldacena, using what's sometimes called the ADS-CFT correspondence of string theory. Okay, this thing was set within string theory. I won't really tell you what string theory is. In the rest of this talk, what I'm going to tell you about is the construction of this one complete, consistent theory of quantum fluctuating spacetime, or one class of complete, consistent theories of quantum fluctuating spacetime that physicists have now hit upon, and that we understand, and what we have managed to learn from this. Okay, so the rest of the talk is dedicated to trying to understand one consistent quantum theory of gravity, really a class of these. But as a preliminary to this question, just in order to understand how interesting the answer is, I will give you a historical counterfoil. That is, the kind of question we're trying to answer appears superficially similar to a question that people addressed between 1930 and 1950. Between 1930 and 1950, people knew of two kinds of theories. They knew that the world was quantum, and they knew that the theory of light was governed by Maxwell's equations of electromagnetism. But Maxwell's equations, as formulated by Maxwell, are classical equations. The goal of putting them together to get a quantum theory of light interacting with charged matter, let's say light interacting with electrons, was an obviously important one of great importance. And between 1928 and 1950, physicists scrambled to try to find the answer. And eventually it was constructed. Roughly 1950, the theory of quantum electrodynamics was constructed in full, in a satisfactory manner. Okay. Now, the actual technicalities of the construction and so on, complicated. People had to understand many things that were unexpected, theory of renormalization and so on. But if you step back and ask, shorn of all the technicalities, we just take away all the technicalities, what was the final theory like? Conceptually, it was very simple. The classical theory of electrodynamics, let me focus on the part of it that is electrodynamical and ignore the electrons. The classical theory of electrodynamics was just a classical field theory with one, or really a small finite number of degrees of freedom at each point in space, obeying classical equations. These are Maxwell's equations, which many of you study. Many of you know. The final theory of quantum electrodynamics is a theory in which, corresponding to every classical degree of freedom, for instance, the electric fields and the magnetic fields, corresponding to every classical degree of freedom, there is a corresponding quantum degree of freedom. And the structure of these quantum degrees of freedom is such that the reduction from quantum mechanics to classical mechanics is automatic in a particular parametric limit. The parametric limit in question here is the limit h bar goes to 0, where h bar is Planck's constant. For those of you who studied this reduction, the automaticity of this reduction happens because of the correspondence principle. Commutators and Poisson brackets are very similar algebraic structures. So in the end, when all the dust is settled, this great technical accomplishment of construction of quantum electrodynamics. Quantum electrodynamics was the theory which was used to calculate the fine structure constant that I showed you about. I showed you a slide, 20 minutes ago. That number with many decimal places with theory and many decimal places in experiment and degrees. Quantum electrodynamics was the framework for that calculation. Magnificent theoretical structure, tribute to human intellect. And yet, conceptually, the structure of quantum electrodynamics is so close to the structure of classical electrodynamics. For every classical degree of freedom, there's quantum degree of freedom. Then in the end, it's almost a little disappointing. It's nothing very new. Now we are faced with a similar question. We're faced with finding a quantum theory of fluctuating metrics. In 1997, Maldacena asked himself the following question. What is the quantum theory of gravity? It's got a name, 2B supergravity, propagating in the 10-dimensional space ADS 5 times S5. Okay, so what do I mean by this? See, our world lives in 3 plus 1 dimensions. 3 space and 1 time dimensions. Mathematically, you can imagine worlds, okay, which live in higher dimensions. And in string theory, there's some special simplicity to worlds that live in 10 or 11 dimensions. So Maldacena looked at a very simple model of string theory, one in which space-time was 10-dimensional. Now, the ambient background geometry of the space-time was not just flat space, as is approximately the case in our universe, but a product of 2 spaces. The first of these spaces is an S5. That's 5-dimensional sphere. What is this S5? This S5 is a very simple thing. It's easy for everyone to understand. You know, an S2, a normal 2 sphere like the surface of a globe, is the locus of all points from the origin in a 3-dimensional space that are unit distance away from that origin. Similarly, an S5 is the locus of all points from the origin in a 6-dimensional flat space that are unit distance away from that origin. This is not a very complicated thing to think about. Many of you can already, in some mathematical sense, picture it. On the other hand, the second part of the space-time is more interesting. This part that's called ADS5 is more interesting, and I won't say much about it, except to point out that this, unlike the S5, is not space. It's space and time. So out of these 5 dimensions that are in ADS5, 4 of these are space and 1 is time. Okay. So there is a theory of gravity that comes to us from string theory, in which the background space-time, the ambient background space-time, is this ADS time 5 cross S5. But space-time is dynamical, so you have more interesting space-times in this theory. Space-time does whatever it does, matter does whatever it does in this theory, and it's an interesting theory. The question that Maldacena asked himself was, what is the full, complete formulation of this gravity theory in this space ADS 5 times S5? Now notice, before we proceed, notice we're dealing with a spherical cow here. Our universe is not ADS 5 times S5. Our universe, as far as we can see, is 4-dimensional. The spherical cow here is 10-dimensional. Our universe has no S5 floating around, and there are many things to say about this. We're not trying to describe our universe. We're just trying to solve a mathematical problem. What is the complete formulation of one particular, apparently well-posed quantum theory of gravity? How do you formulate it? What is its underlying structure? At the end of 1997, Maldacena discovered something very interesting. He discovered that the solution to finding the mathematical theory of quantum fluctuating space-times and this type 2b supergravity on ADS 5 times S5 was not given by replacing all the classical metric fields by their quantum counterparts. That is what this example would have suggested. For every classical construct, like an electric field or a magnetic field, there is a quantum counterpart. And those are the basic objects in the quantum theory. That's how electrodynamics works. That's not how this theory works here. Instead, the final mathematical formulation of this theory was given by a 4-dimensional quantum field theory, whose name is a bit of a mouthful. The name is UN, N equals 4, D equals 4 super Yang-Mills theory, which in some sense lives at the boundary of ADS 5 times S5. So if you've been following my talk, and you've not heard the story before, I'm sure you're puzzled. What I just said sounds like it makes no sense. There are many ways in which it sounds ridiculous. First, I spent the first half of this talk telling you that quantum field theories don't have gravity in them, don't have fluctuating space-times in them. Now I'm telling you the formulation of a 10-dimensional gravity theory is in terms of a 4-dimensional quantum field theory. But doesn't this contradict the fact that 4-dimensional quantum field theories don't have a formulated on a fixed background space-time? There's no dynamical space-time there. So what am I talking about? I also told you that a 10-dimensional theory, the ultimate formulation, the mathematical complete formulation of a 10-dimensional gravity theory was a 4-dimensional field theory. What sense does that make? You're into 10-dimensional physics, don't you need a 10-dimensional formulation? How can that work? I'm going to give you 2 minutes on how it works. You see, this quantum field theory, UN n equals 4, d equals 4 super Yang-Mills theory, is a quantum field theory. It has a finite number of quantum degrees of freedom at each point in space. The only thing that's going to be important for me for this talk is that the quantum degrees of freedom in UN n equals 4, d equals 4 super Yang-Mills theory are n cross n matrices. Okay? So the number of degrees of freedom is a finite number, in this case, in some sense, 16, times n squared. Okay. Now, such a theory with so many degrees of freedom at each point in space, as we increase n, becomes more and more complicated. Because there's more and more degrees of freedom at each point in space. But as you increase n further and further, so that n becomes very large, it has been understood for a long time that when you take this strange limit of n going to infinity, a new emergent simplicity arises in quantum field theory dynamics. This was understood by Toft long ago, the 1970s. The new emergent simplicity goes as follows. You see, it's a consequence of something, of a phenomenon that's not too different from what people sometimes call the law of large numbers. That even if individual things fluctuate, if you take an average over a large number of them, the fluctuation of the average compared to the value of the average is suppressed compared to the fluctuation of each quantity divided by its average by a factor of 1 over square root n, where n is the number of quantities that goes into this average. Now this UN n equals 4, d equals 4 Yang-Mills theory is equipped with the rule that tells you that the only observable quantities in this theory are sort of averages over something like n squared elements. It follows because of that even though this theory is a quantum theory in which things are fluctuating around, the observables, the things you can observe in this theory, the fluctuations of these quantities are suppressed compared to what you might naively think they should be by a factor of 1 over n, which is 1 over square root of n squared. This law of large numbers kind of suppression. And in the strict large n limit, these quantities don't fluctuate at all. The quantum fuzz of these quantities goes away. This means that these theories, that large classes of large n quantum theories in the large n limit become classical. Now this is very interesting. This is very interesting because you see, for a long time we've known of one classical limit of quantum theories. This is the limit in which Planck's constant, Planck's constant, h bar goes to 0. This is a limit in which quantum theory becomes classical theory, and the limit is sort of trivial in the sense that if you know the classical theory, if you know the quantum theory and you can see its h bar, you take h bar to 0, not only do you know that it's going to become a classical theory, you know which classical theory it's going to become. Now what I've told you about is that there is a second independent limit of quantum field theories in which quantum field theory dynamics becomes classical. However, this large n limit is a much more interesting limit, much more interesting classical limit than the h bar goes to 0 limit. And it's more interesting, more complicated. And it's more complicated and more interesting. And as a consequence of this, though you can use general theorems to show that in the large n limit, quantum field theories become classical, it is typically not easy to figure out what classical theory they reduce to in the large n limit. Okay? And for many interesting theories, people have spent decades trying to figure this out. And apart from very simple toy examples, there's been very little progress. it's, I think, fair to say that it was universally assumed that the classical theories obtained from large n limits of interesting enough quantum field theories would be very messy, non-local, useless classical theories. Okay. Now, in 1997, what Maldacena demonstrated is you took this very beautiful quantum field theory, you take its large n limit, it reduces to classical theory, and that classical theory is not some non-local crazy mess. It's the classical equations that govern this theory are the most beautiful equations ever written down, in my opinion, by human beings. And these are Einstein's equations of general relativity. More precisely, Einstein's type 2b supergravity describing the propagation of gravity in ADS type 5 times S5. So what we've just discovered is that we've got a well-defined quantum field theory which in a particular parametric limit, this large n limit, reduces to classical 2b supergravity on the space. In other words, we've discovered the correct, fully consistent quantization of 2b classical supergravity. It's B equals 4, N equals 4 superangles theory in 4 dimensions. Now, what about this business of, these two questions that I asked you at the beginning, I posed at the beginning? How could it be that a classical theory, that a quantum field theory gives you fluctuating space-time geometry? You see, what happens here is this. You take the large n limit of this quantum field theory, and in this large n limit, there are some quantities that are emerged that obey some classical equations. These classical equations just happen to be propagating in some fictional 10-dimensional space-time. Some space-time that was not put into the formulation of n equals 4, d equals 4 superangles theory, but comes out of the solution of this theory in the large n limit. Okay? So this 10-dimensional space-time and its fluctuating nature, its dynamical nature, is not put into the formulation of the n equals 4, d equals 4 superangles theory. It comes out when you are able to solve this theory in a particular limit, namely this large n limit. If you retreat away from the strict large n limit, so n is a billion, but not infinity. Now, this theory is not quite classical, but fluctuations are still highly suppressed. And these highly suppressed fluctuations map to the quantum fluctuations of this 10-dimensional space-time. However, if you work at strictly finite n, n equals 3, then there is no sense in which there is a 10-dimensional geometry. The quantum fluctuations of this 10-dimensional geometry have become so wild that it's stupid to think of this problem in terms of 10-dimensional geometries anymore. There's no sense in which that's really there. All you're left with is the 4-dimensional theory. Okay? Within this model, therefore, there is a sense in which dynamical space-time is an illusion, an emergent notion that has precise meaning only at very large n, but whose reality becomes increasingly tenuous as n is decreased. More precisely, in the fundamental formulation of the theory, there is no 10-dimensional space-time at all. It emerges in some approximation, solving the theory in some parametric limit. This seems to me to be a fundamental insight into the nature of space and time in gravitational theories, one that we're still grappling with and trying to understand better. At a much more mundane level, all of this suggests a completely unanticipated role for theories of gravity within the structures of theoretical physics. As I've explained when I try to explain how you could understand the solution of n equals 4, d equals 4 superangles theory, gravitational theories emerge as the effective classical descriptions of strongly coupled non-gravitational systems. In this case, in the example we studied, n equals 4, d equals 4 angles theory, in the limit of a large number of degrees of freedom. 1 by n corrections to the classical limit yield quantum fluctuations of gravity. Thus, theories of gravity provide an effective large n mean field type description for certain strongly coupled non-gravitational quantum systems. This is by itself a remarkable thing. What we just discovered is that if you are an experimentalist and you're trying to solve some complicated material whose fundamental formulation is given in terms of a large number of degrees of freedom, a quantum field theory with a large number of degrees of freedom, This problem seems to have nothing to do with gravity. And yet, in a particular parametric limit, the best way to solve this problem may turn out to be by formulating it as a theory of gravity and solving the theory of gravity. Thus, quantum theories of quantum gravity become a tool for studying non-gravitational physics. Okay, I'm almost at the end of my talk. Several aspects of the story I've outlined above remain unsatisfactorily understood. To start with, the fact that this complicated quantum field theory reduces to 10-dimensional supergravity at large n has only been established within the framework of string theory. We have never directly within quantum field theory proved this fact. It seems likely that we learn a great deal by filling this gap. We will understand precisely how non-gravitational physics can build up gravitational dynamics. Okay, now, when I started describing what Maldacena had done, I told you he chose a particular quantum fluctuating spacetime, this 2B supergravity on ADS 5 times S5. This was a simple model within string theory and found its full non-perturbative description. Okay, a string theory, this beautiful theoretical framework, has many more simple such theories. For most of them, we don't understand what their non-perturbative framework is. What is the true framework of, let's say, type 2B supergravity in flat space? M theory in 11 dimension. We don't understand what the right non-perturbative description of this theory is. So, we've solved this question of finding a non-perturbative description of quantum gravity for some examples, but only a few examples. We don't have the general story yet. Finally, in order to address the question of the birth of our universe, the question I started my talk with to motivate the study, we want a formulation of the quantum theory of gravity, not in some toy model, not in some spherical Cup model, but in the model of the theory, in the universe in which we live. Does the theory of quantum gravity of the real world lie within the string framework? If so, how do we identify and understand this theory? I don't know the answer to these questions, but I think it's likely that some input from experiment, perhaps from an unexpected source, will play some role in answering this. Okay, so this is the final summary of my talk. I explained to you that quantum gravity, we don't understand we don't have a framework that helps us understand phenomena in which quantum mechanics and fluctuating spacetimes, dynamical spacetimes are simultaneously important. I explained to you that quantum gravity is likely needed to understand the early universe. I told you almost nothing about string theory, but I told you that within this formulation, we found a complete but surprising formulation of one class of 10-dimensional quantum gravity systems, and the complete formulation is in terms of lower dimensional non-gravitational quantum field theory. This result is a great surprise. Space and time in these gravitational theories are emergent notions in these models. There's a sense in which space-time is an illusion. The complete formulation of other gravitational systems, even within string theory, is an outstanding formal challenge. Formulation of the non-spherical quantum theory of gravity of the real world is an even bigger challenge. There's lots to do in coming years. Okay, thank you. I can't hear you.
Sorry, sir. So that was indeed a talk which actually focused on the search for quantum gravity. And I'm sure the attendees must have realized that if there is no theory of quantum gravity, then the universe is just a chaos and it's just random. And so we have certain questions right there in the chat box. So would you like to answer them, sir?
Sure. Okay,
so I'll read it. So I'll
yeah,
read
sure.
it out one by one, sir. So we had a question by Abhishek Kumar. So he says that how long do you see from now that string theory or the M theory, like the mother of all theories, will be developed completely or proved empirically?
Okay. So these are two different questions. The first question is, how long will we take to understand the full theoretical structure of string theory, of the web of theories that goes under the name of string theory? And the second question was, about the connection with the experiment, and the question is about time frames. It seems to me that the theoretical structures of string theory are rich enough to perhaps encompass every theoretical study within physics that has ever been done by human beings. For instance, string theory in some limit reduces to quantum field theories, so it reduces to simpler systems as well in some limits. So the question of completely understanding string theory, it depends on what your standards are. But completely solving it, perhaps we'll never do it. Understanding it in the sense of completely having a first principle understanding of the theory and understanding it at the same level that we understand quantum field theory today, let's say. Who knows how long that will take? We're certainly not there. We certainly don't understand it at that level. And how long it will take, I have no clue. It's just very hard to say. Okay. The question of how long it would take to know whether or not string theory is the non-spherical cow theory of quantum gravity in our universe, that also, how could you imagine it working? Either you could imagine somebody has a really good idea, finds a model, and then makes a prediction like of something that we already know. For instance, the ratio of the mass of the muon to the electron, and gets it right. Then we'll be pretty confident that it's right. Yes. Could happen, who knows? The other way is to find some source of experimental data. So, real answer to both questions, I have no clue. Just don't know.
So I hope the Abhishek Kumar gets answered, but he's still in clue. So moving on to the next question, he's Dr. Ajay Sinha. He asked that string theory predicts 10 dimensions, 9 space and 1 time, whereas M theory predicts 11 dimensions. What does this mean? Like, are they contradictory, or so what's the need of so many dimensions?
Yeah, what is the need of so many dimensions? You see, string theory is a large framework. It's a theory, in a sense, with a large number of vacua. Okay? Now, different vacua in this theory have different properties. Some of these vacua are very simple on one end of this sort of space of vacua and are perturbative, weakly coupled in 10 dimensions. There's this other vacuum that is sort of simple and has 11 dimensions, M theory. But you can have compactifications of these theories. These compactifications can allow you to come down to lower dimensions. So there are also vacua that are 4-dimensional and 6-dimensional. So string theory is a framework with a zoo, in some sense a theory, which has a whole zoo of different vacua, and different vacua have different properties. So one of these vacua has big 11 dimensions, and another class of such vacua have big 10 dimensions. There's no contradiction. What is unusual is to have one theory with so many inequivalent vacua. We've for a long time been familiar with the fact that you can have many different distinct vacua in a single quantum field theory. For instance, the theory of ferromagnetism has this property. But in familiar examples, these distinct vacua are related by symmetries. That's the case in theory of ferromagnetism. So if you know what the physics is like in one of these vacua, you know what it's like in any other. There are now many familiar examples of supersymmetric quantum field theories, which we understand very well, which have moduli spaces of vacua, many different distinct vacua, which are not related by symmetry. So you cannot get the physics of one of the vacuum from knowing the physics of the other one. And so if you lived in one vacuum or the other one, you would see very different kinds of physics. This is the kind of thing that's going on in string theory. And this is part of what leads to the great complexity of the theory, that it's a very rich theory with large number of vacua. One of them is 11-dimensional, several of them 10-dimensional. There are many others.
Yes. So I guess that's answer your questions, Dr. Ajay Sinha. So there's one more question also by Keshav Kumar Jha. He asked that would the search for graviton end the elusive search for the theory of everything, or it will be just another step towards it? So,
well, just finding a graviton itself would not end the search, right? I mean, in some sense, we've already detected gravity waves. Now, of course, those are classical objects. If we manage to find some evidence of quantization of the gravitons, that would be nice, but would not end anything. Because any reasonable quantum theory of gravity has gravitons in them. The gravitons are like the free gravity particles. The question is what happens when they bang and interact with each other and so on. Maybe the questioner really meant to ask, would the theory of quantum gravity end the search for the theory of everything, not just gravitons, but quantum gravity? If that was the question, of course, probably yes. You see, I'll tell you why I say so. There is this interesting feature in string theory that is not shared in quantum field theory. And that's this. Suppose you have a quantum field theory, which describes, for instance, an electron and a muon interacting with the electromagnetic field. The electron has mass m1, the muon has mass m2. Now you do more precise experiments and you see that actually the mass of the muon is not m2, but m2 plus delta m2. You were modeling it a little wrong. There's no problem. In your model, you can just change the parameter. You can change m2 to m2 plus delta m2, and that will be the model for this new theory. So there are, the phenomenon I was trying to explain is that quantum field theories have typically a few, just a finite number, but a few freely adjustable parameters that you can adjust to whatever value you want to fit your experiments. This is not the situation in string theory. String theory, quantum theories of gravity, we understand, are very tightly constrained by consistency. And if you take the theory, you take it all at once. If you've got a theory of quantum gravity with an electron of some mass and a muon of some other mass and various other particles, that comes from string theory. If you then try to just keep the rest of the theory as it is, but change the mass of the electron a little bit, if you do that by hand, you will land up with a theory that is nonsense, that is not consistent anymore. Okay, so string theory is a very tight theory. Everything's tied to everything else. You can't take one sector out and fool around with something else. So if the theory of quantum gravity that we find is like the string theories that we sort of understand, I suspect that the answer is yes, we will have found everything if we find the quantum theory of gravity.
So the search for graviton may end the elusive theory of everything. So,
well, gravity, not graviton.
Yeah, sure, gravity. So next question is by Neil Vadodia. He asks that can naked singularities be a good candidate to get data on quantum gravity?
Oh, this is a great question. Yes. Okay. If naked singularities exist and we can in a reasonable way access them, then they are likely to be a great source of information on quantum gravity. Okay. However, there's a big if involved here. Now I don't know the background of the questioner, but he might know that there are two views on this question, whether naked singularities can or cannot form in reasonable theories of gravity. My ex-colleague in TIFR, Pankaj Joshi, was one of the strong proponents of the view that they can form in reasonable theories. However, there are other strong views on this, supported by some amount of evidence. I don't think it's clear that that naked singularities can form with reasonable matter. But if they could, and we could access them, they would be a great source of information for quantum gravity.
Okay. So we'll take just one last question. So this question by again Amish Mittal. He asked that has any researcher ever tried to limit the degrees of freedom? Like assume that every body in the universe has only 1 or 2 degrees of freedom. So has it helped in proving some results, basically using a reduction principle to understand all these stuffs?
Okay, this is a very interesting question. Let's see. Has anyone tried to suggest that there are... I'm going to change the question a bit. I'm going to change the question to... has anyone tried to model the universe as a universe with a finite number of degrees of freedom? Okay, perhaps this is close to the spirit of the question. 1 or 2, certainly not. Certainly not. But maybe a finite number of degrees of freedom. Now, see, there is this remarkable Bekenstein-Hawking formula for the entropy of black holes that tells you that the number of degrees of freedom, that suggests that the number of degrees of freedom inside a black hole is it's the area of its event horizon divided by 4 times Newton's constant times Planck's constant. Now the same formula, there's a lot of evidence that this is true. Now the same formula, if applied to the space called de Sitter space, suggests that the quantum theory of gravity in de Sitter space is governed by a Hilbert space with a finite number of degrees of freedom. And now, actually, let me say more clearly. When I say finite number of degrees of freedom, I mean a Hilbert space of finite dimensionality. This is really strange, right? This is really strange because if you take a single harmonic oscillator, okay, if you take a single harmonic oscillator and you ask what is the dimensionality of the Hilbert space of the single harmonic oscillator, you find that the answer is infinity, right? Because you have states of all energies. However, applying the Bekenstein-Hawking formula to de Sitter space suggests that perhaps the physics of de Sitter space is governed by a finite dimensional Hilbert space, which would have all kinds of consequences. There would be a certain graininess in this physics because of this finite dimensionality of the Hilbert space. All these ideas are rather speculative and have never been made precise, but that's the closest that I can come to that reminds me of what Amish is asking. If Amish is interested in these ideas, there are papers by Tom Banks over the last 10 or 15 years that he could look at.
Okay, sure. So we can limit the degrees of freedom, but not 1 to 2. Like 1 to 2 is a very meager amount. So
well, whether we can or not, there are some suggestions that in some spaces we can. Actually, something one should say about this is that it appears that the space we live in our in the real world is de Sitter space. So maybe the real world lives in a finite dimensional Hilbert space, perhaps, maybe.
okay, sir. So there's one last question from my side, sir. So like I want to say, like, people these days are very skeptical to take up careers in basic science. So how can we as engineers contribute to India's advancements in physics and like contribute to the theoretical part of it?
Well, in several ways. The first one is the obvious one, which is, in some places, for instance, in Princeton, the distinction between the electrical engineering department and the physics department is quite the boundaries between these two are quite porous. Raveen Bhatt, for instance, a very eminent theoretical physicist, works in the electrical engineering department there. So, there's a continuum between engineering and physics, and you can be anywhere in this. Of course, one way that engineers most naturally collaborate with physicists is in instrumentation or in building equipment. But, more interestingly, I know from my own experience that often people who are studying engineering sometimes have this actually wanted to study physics. They just don't do that because, as you said, you feel that it's a dangerous thing to do and there's not much future scope. Well, I think the best way you can contribute to the study of theoretical physics, if you really, really want to and you feel a passion for it, is to join it. And it's not uncommon for engineers, after finishing their engineering, to then join a PhD program in physics. For instance, in TIFR, several of our students come from engineering colleges. So if you feel this driving passion to try to understand, this driving desire to want to understand physics, the best way to contribute is to join the search for physical law.
So, like we'll think about it, and maybe we can join TIFR or any other institute who like studies like science. So that's all. We are done with the questions. So like your energy is really commendable, and the way you had made it explain certainly had intrigued many of us studying science or taking theoretical physics as a career. So we are truly blessed to have such an eminent personality as a part of our guest lecture series. I love to extend gratitude on behalf of whole team Celesta and IIT Patna to you, sir, for taking out time from your schedule to mentor and guide us. So the knowledge that viewers have gained today was exceptional, and Team Celesta is grateful for that. Thank you, sir.
Okay, thank you for having me. And again, I'm sorry I can't come and meet you guys in person. That's much more fun, but
Yes,
maybe
sir.
when circumstances allow it. Okay,
Yes.
bye.
Okay. Thank you, sir. Bye, sir. So before we wrap the session, let me tell you about the exciting events which are being conducted by Celesta this year. Are we alone in the universe? The most interesting event which actually amalgamates our interest in astronomy and the creativity you offer. This event is running live and the deadline is 24th December, as you see in the screen. Quest Iron, a series of 5 science tech quizzes being hosted on Dare to Compete website. Today we have the fourth quiz at 8 p.m. Do join us now. Solid Design, the ultimate designing challenge for civil engineers. Case study that test capabilities and skills like data analysis, logical deduction. Vivus Chroma, an event where you get your creativity flowing and produce a short animation video on the topic dream or reality. One-on-one debate, an event that calls upon both your logical reasoning and oratory dominance, everything in a heat of argument. Innova, so just bring out your chemistry knowledge and design a poster for your idea using your innovations. NJAT, the most fun event in Celesta 20. I like this is our own online treasure hunt. So do join this event. Do register for it. CAD Maestro, building components on SolidWorks and assembling them, and the most awaited robotics operating system workshop and hackathon. So with a grand bumper prize of 60,000 rupees, like this is scheduled in the mid-January. For all these events and guest lectures and more details, visit our website www.celesta.tech and register now. Also, book your official Celesta 20 merchandise. That is the super cool tees at just rupees 400 for one tee and rupees 750 if you want two t-shirts. And also get a free delivery at your doorsteps. Order now on the link given in the description. So the heartbeat races as we reach the end of this session because now begins the countdown for tomorrow's guest lectures and events. Carrying all the butterflies in our stomachs, let us all witness the journey beyond the horizon. The fun and excitement only grows as each day ends, and the journey to diving deep into the cyberverse beckons as closer. Thank you everyone for joining with us today. If you found this lecture helpful, don't forget to share with your friends. The recording will be available in just a few moments. Let's catch you tomorrow with more exciting events and awesome guest lectures. Till then, have a nice day and goodbye. Bye.